blazars are really bright, and we think that they're really bright because, well, there's certain things we know about AGN in general. AGN is you've got a central black hole and it's got an accretion disk, and that's powering its emission, and they create jets. So two jets going in opposite directions, and we believe that a blazar is when we're looking at that jet, but along the jet. Okay, so we're looking into the jet. So it's very hard to accelerate ultra-energy cosmic rays because we need strong magnetic fields to confine the particles, and we need shocks that are very fast at the same time. So one possibility is that within the jet, okay, you've got different Lorentz factor flows, okay, and the particles can sample different Lorentz factor flows. We've heard at this meeting about it a little bit. And in fact, what's interesting about such a scenario is you can then have strong magnetic fields and have strong scattering velocities, which is what we needed to have fast acceleration times. And that's at least is one possibility of how to accelerate ultra-energy cosmic rays in a blazar jet.
If I may just add, of course, for cosmic rays, what's different from radiation is, of course, they can be deflected by magnetic fields before reaching us. So if blazars can accelerate ultra-energy cosmic rays, the ones that are pointed away from us, that is, the objects that won't be described as blazars, can also be accelerating in the same way, and they can contribute. There's some argument as to whether the cosmic rays themselves are really beams or not, in terms of the contribution to us. So it's when you say how blazars can accelerate ultra-energy cosmic rays, it's a more general question of whether AGNs with jets can accelerate cosmic rays. So about the radiation processes, the mechanisms, we think we have some, fairly, at least there's an important component of radiation emitted by electrons that are accelerating jet. And there's some controversy as to how much there's also contribution from protons, hadronic emission processes. But then further beyond that, there are still many questions. How the particles accelerated, one generic mechanism, of course, is acceleration in shocks along on different locations along the jet. But this is still not entirely clear. There are issues. A more bigger question is how, well, this is thought to come from the jet, but ultimately how the jets are made is still a big open question. Actually, I can say it's probably one of the biggest unsolved problems in astrophysics. Many people think that magnetic fields are somehow responsible. So if I may, the ideal goal would be actually from the observation of blazars really to try to give an observational answer to how the jets are being produced. But there are some ways to go before that. But we should, this is one thing we should be thinking about.
On a personal note, what excites me about blazars at the moment, and that would be variability. We see very short time variability at high energies, which is surprising. It seems to indicate that the acceleration site of these high energy particles is occurring quite closer in than we used to think, actually. And a lot of the scenarios that we've developed in the past to describe the emission process don't seem to work anymore when we include this variability information. So if I was to guess for the near future, what we're going to learn about blazars, it would be something like, from the time information, we're going to have to rewrite some of our understanding of the acceleration process in AGN and lasers.
Well, they are being extragalactic sources that is located far away from us. They, in different ways, they can be used as beacons to probe things intervening between the source and us, and when it's the so-called extragalactic background light, photons, gamma rays of high enough energies can interact with low energy photons that constitute this diffuse background light and get absorbed, and which means that actually we can turn this around, and by looking at the effects of this absorption in the spectra that we observe in the gamma sources, we can learn how much low energy, well, this is more infrared or optical light, diffuse light there is in the universe, which can be very difficult to do very directly, because in the optical and infrared there's a lot of foreground emission, instrumental issues, which can be very difficult to do directly. So this indirect measurement is certainly a very useful complementary probe.
There's another problem that about AGN in general is their activity. When you look at certain local, our nearest AGNs, right, like SENE, M87, we see that they're very underluminous in terms of their Eddington luminosity, which is very curious. They have, say, 10 to the minus 5 Eddington. Okay, so they're ridiculous. And also Sagittarius A star in the center of our own galaxy. And we don't know why we see distant blazars, and they seem to be very active. We see local ones that are very underactive. And I'm trying to connect this now to, you said fundamental physics. Well, how objects accrete and why they go into low states and then strangely go into high states, that needs understanding. And I guess that at least fundamental astrophysics, I don't mean fundamental particle physics, but that certainly needs explaining, and it's a real mystery. Actually, one interesting thing to add to that, because we're learning lots all the time, is there's also an ongoing debate at the moment actually about Sagittarius A star and its own history. There's X-ray information that we see from Sagittarius A star, from reflections of X-rays and molecular clouds surrounding Sagittarius A star, and there's a delay time of the propagation of the photons hitting the clouds and then coming to us. And it seems from just those reflections that Sagittarius A star in the recent past, let's say in the last few hundred years, was much more active than it is today by a factor of 1,000 or more. So, yeah, we need to understand Sagittarius, or we need to understand AGN activity in general, and it'll, again, future observations should improve our understanding, I hope.
I don't have an easy answer at this moment, of course, but it's something worth thinking about. Certainly, it would tell us something. For example, if it's coming from within the jets and that, like the sources that are blazars, it would certainly tell us that at least there's an important component of protons in the jet, which is actually not even clear at this moment from the other pre-existing observations. Some people say that actually the jets in AGNs are mainly electrons and positrons rather than electrons and protons. So at least it is, if we can really prove that the cosmic rays come from AGN within AGN jets, it is an important piece of information. Yeah, and this will, of course, ultimately also tell us something about how the jets are made.
When you do simple calculations for acceleration times within any object, you give it a dimension and you give it a magnetic field and you give it a velocity of the scatterer, you can work out the maximum energy that that particular object could obtain. And what's interesting is when you do that sort of calculation, the very limit of what you can reach is what we see, which is curious because that you did the most simple and in some sense optimistic calculation, and you actually can only just explain observation. So that seems to suggest, and by the way, it's not the first time we're surprised. If I go back to supernova remnants and I look at the variability, we heard at this meeting, the variability time in supernova remnants, which is also telling us about the acceleration time in supernova remnants, they're also acting in a sort of optimal regime. They're accelerating, it's like they've been designed to accelerate. There's certainly lots to be learned about the sources of ultrasonic cosmic rays, but the fact that we have ultrasonic cosmic rays and the fact that they're so hard to explain in terms of our present understanding of how particle acceleration works is intriguing.